Commutative property of vector addition. Welcome, everyone. Today, we are going to explore a very important concept in vector algebra known as the commutative property of vector addition. Now, when we talk about a property in mathematics, we aren't talking about a fundamental rule or principle. In this specific case, the commutative property describes how the order in which we add things affects our final result. To make this easier to grasp, let's look at something you are already very familiar with: simple scalar numbers. You know from basic arithmetic that 2 plus 3 gives you the same result as 3 plus 2. It doesn't matter which number you start with, the sum remains the same. As we move through this lesson, you will see that vector addition follows this exact same rule. We will be proving this mathematically and visually in the upcoming slides. Definition. Now that we've introduced the idea that vectors behave similarly to the simple numbers we use every day, let's look at the formal definition. The commutative property of vector addition essentially tells us that the order in which you add two vectors does not change the final resultant vector. In other words, it doesn't matter which vector you start with, the end result is exactly the same. To put this into mathematical terms, for any two vectors, a and b, this property is expressed as a plus b equals b plus a. As we move into the next few slides, we are going to prove why this is true using a geometric approach. Geometric proof. Step 1. Set up the geometry. Now that we have established the definition of the commutative property, let's move into the formal proof. To prove this property mathematically, we are going to use the geometry of a parallelogram. Please visualize or draw a parallelogram and label the vertices A, B, C, and D in order. To begin our calculation, let's assign specific vectors to represent the sides of this shape. We will let the vector from point A to point B be represented by vector A, and let the vector from point B to point C be represented by vector B. Geometric proof. Step 2. Finding the resultant via the first path. Now that we have set up our parallelogram $, and labeled our initial vectors, let's look at our first path. According to the triangle law of vector addition, if we follow the path from point A to point B$, and then continue from point B$ to point C$, the net displacement, or the direct shortcut from our starting point to our end point, is represented by the vector AC$ with an arrow over it. In mathematical terms, we write this as vector AC$ equals vector AB$ plus vector B$C$. Now, if we substitute the specific labels we defined in the previous slide, where vector AB$ is vector $, and vector B$C$ is vector B$, we get the simplified expression. Vector AC$ equals vector $, plus vector B$. We will refer to this as equation 1, and we'll need to compare it to a second path in just a moment. Geometric proof. Step 3. Utilizing parallelogram properties. Now, to move forward with our proof, we need to look at the fundamental properties of the parallelogram we set up in the previous slide. One of the defining characteristics of a parallelogram is that its opposite sides are both equal in magnitude and parallel in direction. This is a crucial piece of information for our geometric argument. Because of this property, we can establish some direct equalities between our vectors. If we look at the side we labeled as vector B, which is the vector from B to C, we can see that the opposite side, the vector from A to D, is identical. So we can say that the vector AD equals the vector BC, which we have already defined as vector B. Similarly, if we look at our first vector, vector AB, which we called vector A, its opposite side is the vector from D to C. Therefore, the vector DC is also equal to vector AB, or simply, vector A. Keeping these equalities in mind will allow us to calculate the second path to our destination in the next step. Geometric proof. Step 4. Finding the resultant via the second path. Now that we have established the properties of the sides in the previous slide, let's look at the second path across our parallelogram. Instead of starting from point A and moving towards C via point B, let's consider the path from point A to point D, and then from point D to point C by applying the triangle law of vector addition once again to this new path. We can state that the vector AC is equal to the vector AD plus the vector DC. Now, if we substitute the specific vectors we identified in the last step, remembering that vector AD is the same as vector B, and vector DC is the same as vector A, we arrive at our second important result. Vector AC equals vector B plus vector A. We'll label this as equation 2, which we will use in the next slide to reach our final conclusion. Geometric proof step 5, conclusion. Now let's bring everything together to reach our conclusion. If you look back at what we just did in the previous steps, we have two different ways of looking at the same diagonal. By comparing equation 1, where we followed the first path, with equation 2, where we followed the second path, we can see that both paths lead us to the exact same resultant vector, which is a C. This brings us to our mathematical proof, A plus B equals B plus A. Because we have shown that the final vector is identical regardless of the order in which we added the sides, we can officially conclude that vector addition is commutative. This confirms that the order of the vectors does not change the final result, a concept we are about to see applied in a real-world navigation example in the next slide. Real-world example, navigation. Now that we have mathematically proven the commutative property using the geometry of a parallelogram, let's step away from the abstract equations and look at how this applies to a real-world situation. Imagine a drone moving across a flat, two-dimensional plane. Let's look at scenario A first. Suppose the drone starts at a base point and first moves 5 kilometers toward the east, which we can represent with the vector A. From that new position, the drone then moves 3 kilometers toward the north, represented by the vector B. If we want to find the drone's final position relative to where it started, we calculate the resultant vector, which is A plus B. Now let's switch the order and look at scenario B in this case. The drone starts at the same base point, but this time it first moves 3 kilometers north, using vector B. After that, it moves 5 kilometers east, using vector A. To find the final position here, we are looking at the resultant vector, B plus A. If you observe the outcome of both scenarios, you will notice something important. Despite the different paths taken, the drone ends up at the exact same geographical coordinate in both cases. This perfectly demonstrates our lesson. The order of the displacements does not change the final position. This practical application shows that the commutative property isn't just a rule for symbols on a page, but a fundamental truth in navigation. However, as we will see in the next slide, we must be careful not to assume this same flexibility applies to all vector operations, such as subtraction. Common mistakes. Now, before we wrap up our lesson, I want to pause and highlight some common pitfalls that students often encounter when working with vectors. It is crucial to address these now, so you can avoid them in your upcoming exams. First, let's talk about the danger of confusing addition with subtraction. We have just spent the last few slides proving that vector addition is commutative, meaning the order doesn't matter. However, please be very careful. This rule does not apply to subtraction. A very common error is assuming that subtracting vector B from vector A is the same as subtracting vector A from vector B. It is not. In vector algebra, vector A minus vector B does not equal vector B minus vector A. In fact, if you reverse the order in subtraction, you actually get the negative of your original result. Specifically, vector A minus vector B equals negative of the quantity vector B minus vector A. Second, watch out for the temptation to ignore direction. When we were looking at the drone example in the previous slide, we saw how the path matters for the journey, even if the destination is the same. Sometimes, students treat vectors as if they are just simple scalar numbers. Remember, a vector is not just a sum of magnitudes. When you add two vectors, you are combining both their magnitudes and their specific directions. If you ignore the direction, you lose the very essence of what a vector is. Finally, pay close attention to your vector notation. Precision is key in mathematics. You must clearly distinguish between the vector ob, which represents the movement from point A to point B, and the vector BA, which represents the movement from point B to point A, these are not the same. In fact, vector ob is equal to negative vector BA. Keep these points in mind as we move into our final summary of the key takeaways. Key takeaways. First, remember the core principle we've been discussing. The commutative property ensures that vector A plus vector B is exactly equal to vector B plus vector A. This means that when you are adding vectors, the order in which you combine them simply does not change the final result. Second, let's reflect on the geometric proof we walked through using the parallelogram. We demonstrated that this property holds true because the diagonal of a parallelogram remains the same, regardless of whether you follow the path from the first pair of adjacent sides or the second pair to reach the opposite vertex. Whether you travel a long path then B or B then A, you always land at the same destination. Finally, it is important to understand why this matters in practice. This property is incredibly useful because it simplifies complex vector calculations. It gives you the mathematical freedom to rearrange the order of addition, allowing you to group vectors in whatever way is most convenient or easiest for your specific problem. All right, we have reached the end of our lesson. Let's wrap everything up by reviewing the key takeaways from today's session. That concludes our lesson on the commutative property of vector addition. Keep practicing these geometric visualizations, and I will see you in the next session.